Hi, Lia. Thank
Hi.
you so much for doing this interview. Before we start, may I ask you to briefly introduce yourself in terms of your background, education, research interest, and
Lia,
work?
I'm a current third year now, PhD student at the University of Oxford. I research a few different sub areas in quantum computing, mostly using quantum graphical calculi, so diagrammatic formalisms for education. I did. I out of high school, I applied to computer science programs,
Mhm.
and then somehow I also became a physics major during my undergrad. And then I was a bit new to physics at the time. So I was trying to look for what can I do in both computer science and physics. And so I got it in my head, maybe I should try learning about quantum computing. It sounded really interesting. It was a really different way of thinking about computer science that I just not thought of. Just had trouble wrapping my head around because it was very different. Part-time in a few different jobs throughout my PhD. I enjoyed having some other ways to be involved in gain more experience other than direct research topics. So before I taught cubic by cubic. That was my first part-time job during my PhD. And then I worked part-time at IBM Quantum Education. And now I work part-time as a research engineer at Quantinuum's Oxford branch. So I was really excited that finally I could get a part-time job after the pandemic that is in person. And that was really exciting to actually have an office there and meet people in person. So that's been really fun.
So you got your bachelor's degree in computer science and physics from the University of California. How come you have decided to pursue a degree in both computer science and physics? So what was your bachelor's thesis?
Degrees are in computing and in physics. I started off as a computing undergraduate, and then I tried to join in a physics majors only class. At the time, I thought, okay, maybe I hadn't known what physics was before 12th grade. In fact, I never took a course on it, and I clearly had wrong misconceptions about what physics was until my 12th year, so final year of high school. And you apply to college at the start of your 12th year, so it just wasn't really something I had exposure to until you know, I want to say for many people it would have been too late to decide what you want to do at that point. But actually, in the U.S. system, compared to other countries, you can actually change majors and majors, and there's a lot more flexibility for that in the U.S. College system.
I see.
So, what this consisted of was during my first year undergraduate, I attempted to sit on a class by patiently waiting for the professor at some college lunch where she talked to another professor about goat cheese. And I was excited she was very passionate about goat cheese, but also I didn't know when to interrupt. I'd like basically not really ever talked to a professor in any context before, and so just even how to approach. I was just sitting there eating my lunch, trying to figure out when should I interrupt. But also, this is like their lunchtime. I don't know, maybe no one worked during the lunchtime. And so, but finally, I realized she had to go. And so she said to meet me in her office. And that was quite scary because an office, like in high school, teachers don't have offices. So that was the first step into literally first step. And then she gave me a pop quiz on integrals on the spot to test if she thought I had an adequate math background for the course. Just because it's quite common to do in US universities, but I hadn't expected when I walked in that day that I would be tested.
So was that task hard for you that she gave?
It was actually quite a precise test. It just tested whether or not you have learned something. So it's kind of if you it was just to get a sense of that.
And basically, what was your bachelor's thesis about? Well, was there some specific topic you wrote about, or?
That comes way later. Because let's see. So kind of on the spot in that office at the time, I had just wanted to sit in on one course, all computer science major, so required to take one course, at least one course in physics class, but it's intro to physics, and I had wanted to do more physics. I was just more curious about it. And on the spot, like the professor just said, "Oh, this class is for majors only, physics majors only. Do you want to do a physics major?" And I just stared.
You don't know?
Sure.
Yeah.
Why I said that at the time because clearly I did not have time to think about it. It was like on the spot, but that's clearly what I like. The idea was there now. It just hadn't been even. It hadn't even occurred to me honestly. Until that moment. So I'm really grateful for that. Like there were times when I regretted it, wasn't sure, and like looking back, it was like one of the best things that could have happened. First research experience and for multiple years was in Professor Dave Patterson's group at UC Santa Barbara. How I joined that group was quite interesting actually. Another really lucky thing was I got this email from actually the same professor. This was summer after my first year, and the email was just like, "Oh, I guess casually recommended you for a new lab on campus," and I was like, because I had absolutely zero research experience and not even knowing what research was. I had the idea, okay, maybe I knew research was possible for undergraduates to do, and I knew maybe I could do it maybe in my fourth year if I'm quicker, maybe third year. And so to start in my second year was, but she already recommended me, and I was like, well, I don't.
You cannot quit now, right?
It would be hard to say no. Like I should at least like have a conversation. With the person. I say the person because the email literally did not say what group or who or what. No name, no group, department, research area. It said nothing. It just. I see. It's just a new lab on campus. I was like, what is this? There's no information.
Was that scary for you? This new experience?
It was. I think it was quite scary in the beginning for sure. There was different parts that were scary, but I think the scariest part, well, over a long time. So it wasn't like there was of course the initial scariness of like, what is this lab about? But over the first, I would say 6 to 8 months, I think that the problem I was working on was really hard.
I see.
Or it felt really hard because it had, I would say, hadn't been solved, and so, there was a huge learning curve. So for 6 to 8 months, I think I just made plots that made sense to no one, not even myself. The project was really interesting. So I love talking about it. This project is. Imagine you have a machine that you could put anything you want. When you say anything, like in terms of like chemistry, so you can put any liquid that can become a gas or any gas into it, like it can become a gas by methods of boiling. And then chromatography. But anyway, and then you have these molecules inside your chamber. Oh, I should do this. And then. This is a microwave spectrometer. So the high-level idea is that you shoot microwaves at these molecules, and then the microwaves bounce off, and then you collect them in these microwave horns, and then you take a Fourier transform of the signal that you get, and that's a spectrum.
Oh, I see. So it sounds very interesting. It
was really exciting. It's like, whoa. The whole thing that is. I guess scary is that the first thing you hear when you enter the lab is just which is just the sound of all the helium pumping to keep these that device at about 6 Kelvin. So so that you're very used to it after a while. I actually found it quite calming after a while, but I know some people never get used to it. Just don't.
As a quantum undergraduate researcher at IBM and Princeton, can you talk about the projects you worked on and what was that experience like for you?
Yes. I realized I didn't actually say what my bachelor's thesis was about.
Yeah, okay,
but it was about. Oh no.
Yeah.
It was really different. That's why I thought to give perspective to how different it felt at the time. So my bachelor's thesis was when I joined this Professor Dave Patterson at UC Santa Barbara's microwave spectroscopy, and they also have other experience in atomic, molecular, and optical physics. And, so it's kind of these main two experiments at the time that we were setting up or running the. And so we wanted to run algorithms for this. I'll just kind of call it a box.
Yeah.
So how I think of it, how I abstract it. So I came in with a more computer science perspective of algorithms for microwave spectroscopy to determine molecular structure.
Okay.
So that was pretty much the name of my bachelor's thesis, and it was really exciting. It was like, oh, this is so cool. We're going to have like this box that can scan anything you dump into it and then tell you what it's like, draw the shape of the molecules inside for you, even if it has no idea what the molecules are.
Right.
That was the idea. Of course, in practice, like people didn't even know how to, even if you know even if you have like a perfect pure sample, like only one type of molecule and nothing else. It's still really hard for the machine to be able to identify the molecule.
Right.
When we say identify, this is a quite specific notion to microspectroscopy, which is because at a cold enough temperature, the molecular Hamiltonian is basically the leading terms are just moments of inertia, due to moments of inertia, and then so you can approximate any molecule as these three numbers, the 3 moments of inertia, and the other higher order terms in the Hamiltonian, so like vibrational interactions, these things aren't as present in the populations of the state transitions in the molecular spectrums. So it's the specific microspectra is kind of in the energy range of rotational spectroscopy, so it's also called that as well. So this actually boiled down to looking back at kind of computer science problem, even in this physical chemistry and chemical physics. So that's really interesting. Yeah.
Okay, so you worked as a quantum undergraduate researcher at IBM and Princeton. Can you talk about the projects you worked on and what was that experience like for you?
Yeah. That was a really cool experience because at the time I had this like dream to be at the time I called it a quantum computer scientist. And I didn't have any idea what that would look like. And so this was my first step into, have not just like establishing this identity, but really transitioning into knowing like seeing it in action, to see. So the first time I entered the IBM TJ Watson building, it's a curved building, really, kind of half circle shape, which is, I don't know how practical it is, but it looks really cool. That's about 2,000 people working there.
Wow.
So the first time I was like, wow, this is a large research center. That as an undergraduate, just seeing people like, dashing around and like you get like a snack bar, like this kind of environment, and people working really hard at that. That was a really cool thing to see. I didn't talk about the projects, but so the QRIP program, so the Quantum Undergraduate Research at IBM and Princeton program, is split into roughly 2 halves. One half at the Princeton University, and one half at IBM.
Okay.
IBM Quantum in New York, up in New York, And the projects we worked on, so at Princeton, I was supervised by Professors Michael Martinosi and Steve Lyon, and then most of the I also got a lot of supervision from a postdoc at the time, whose name is Yipeng Huang, Dr. Yipeng Huang. Now he's a professor at Rutgers University. and they were grouped as quantum computer architecture research, and in fact, we're part of this larger collaboration called EPIC across multiple universities. So that was also really cool to see. Wow, this is large-scale effort to really bring quantum computers from bridge this gap between the hardware and all the things we want to achieve.
Yeah.
So the projects I worked on were, let's see. So at Princeton, we called it statistical debugging for using assertions.
Okay.
So one notorious problem with quantum programs is that it's really hard to debug.
Yeah.
So this could be in multiple ways, but for example, if you wanted to print out the quantum state at any point, that's not really something that it's not classical information. You can't just read it out. And even just tomography is quite expensive. And so it's you could have bugs that are really non-obvious and hard to find, and just so we would use assertions as a way that in the middle of your circuit, in theory, hardware or software, or just software simulation, you could stop the circuit and do some measurements, some easy measurements, just to test basic correlation that could, but implemented into IBM's Qiskit open source programming quantum programming language, so that these tests could be done.
Yeah.
There's two projects that were because that was the Princeton project, and then we switched over. The 10 of us that year, we were the first year of this program, so we actually didn't know what to expect. There wasn't anyone we could ask that had done previous years, and then pandemic happened, so there wasn't years after us except online. And then now in person again. So this project at IBM, I would say they gave us a lot of flexibility to choose our projects in the software. Those of us who did more software stuff, and out of the QA entrance cohort. So the first week we wrapped up this quantum statistical debugging with assertions for quantum programs. And then the second week onward, so like for the a bit more than 3 weeks, what I implemented was a parser and transpilation pass in Qiskit that went from Qiskit's quantum circuits to the ZXcalculus Python package called physics and back.
I see.
So it could optimize while in physics. This is actually a project that bridged between two open source repositories. So it's kind of hard to maintain because both these repositories are changing naturally in their open source way, and so support things between repositories is useful, but like it's not. It's up to people on both ends of the open source repository to kind of keep that updated. Actually, the reason at the time, the number one reason why that was not, this part was not incorporated into either repository. It did have code in both repositories to connect them together and do parsing on the physics end and the transpiler pass and the Kukina. But the main reason why this code couldn't be put in, like literally import statements in Qiskit from physics, was at the time physics was not under the Apache 2.0 license, but Qiskit was.
I see.
So at the time physics was on the GPL license, and we actually had to talk to lawyers within IBM. Well, not I didn't, but my manager who had worked in the software team did. And the answer he got back was just, it's not possible. It's legally, you can't do it. To pull in GPT license into Apache 2.0. So this is something that's very specific, but to see, to work on something and see that it's not possible for reasons that are not that are not because of the science or because of the research, or because it was for this kind of reason, was I guess a bit disheartening at the time.
I see. Okay, so if you want, we can move on to the next question. Yes. So so what is ZXcalculus and why is it getting much attention lately?
Yeah, I thought this was related because the last project I just talked about, physics, is a Python package for the ZXcalculus, and so I actually came up with many definitions for ZXcalculus. So I guess it's easier to read them here. So I can say this is what I said. A few days ago, I gave a guest lecture for a grad course at the University of Pennsylvania in a grad course in quantum information. So I was thinking, how should I even start? What is ZXcalculus? That was the question of. It really depends on what it's being used for, what it's being used for, or studied for, or and in the historical context. Right. So here's 4 different definitions of ZXcalculus I just made up, just in an attempt to convey this. So the first one I wrote as the historical definition would be a graphical calculus for the special commutative dagger Frobenius algebras of interacting Z and X observables. Okay, it sounds quite complicated. It's a mouthful. This is the historical definition because ZXcalculus came from the field of categorical quantum mechanics, and the category theory here gives a very precise definition to every one of these words in this definition. However, this definition is nonsense to people who we call it abstract nonsense. Describe when you talk about category theory to someone who doesn't know about category theory. And, I'm not very familiar with category theory, so it's actually extremely intimidating definition. But this is the historical definition. You can see many of the earliest ZX papers. Have this language. In fact, the whole paper is filled with this kind of code stuff, which is quite interesting when people are it makes it less accessible to come. So the category theory is useful for formalizing all these algebras that are really what's the heart or core of the calculi into these diagrams that have these like this underlying formalism. But so the semantics of the diagrams are formalized in this way. It's proper, but at the same time, once you have used category theory to translate the quantum information into the diagrams, once you define the diagram, the diagrammatic graphical calculus, you don't need to know the category theory. Okay. So you can either derive the axioms of the calculus, like comparing the axioms like directly, or you can you don't need to know category theory to use the results that arise in category theory. So that's the first definition. So we have 5 definitions. I put 4. Maybe there's more, but this is just the second one I put as the ZX calculus and the ZW calculus, the ZH calculus, a few different quantum graphical calculi. These ones are all axiomatizations, different axiomatizations of cubic quantum mechanics. Okay. So you can kind of one of the most referenced or well-known papers was by Amar Harney and Harney's papers, Hrvoje and Kangfang, which is their paper on it's 2 different axiomatizations of cubic quantum mechanics, and this is about the ZX calculus and the ZW calculus. Yeah. So what is the difference between the 2? The difference is what you choose as the generators, and so the the nodes of your graphs in the calculus. I see. Okay. So how they're defined, and you get different algebras. So the ZX calculus, the more well-known of these 2, or these 3, I guess, because there's 3 some paper by Chichuan and Coret and Emmanuel dropped all of them, not butchering the French names, said that there's just 3 cubic quantum graphical calculi that are I guess non-trivial that have this bialgebra rule, so they just tested this specific type of rule, and then and some other restrictions, and said ZX, the interaction between Z and X observables, the interaction between Z and the Z observable on the W spider, which you can think of the W spider as like sums. That's one way to think about it.
I see.
And probably it's hard to say the precise definition here, but the interaction between the Z spider and the we call this the H box. So this is, if you generalize the Hadamard gate, instead of having one input wire and one output wire, but you can bend the wire so it has any number of wires, 0 or more, and you can bend them any way you want.
Right. So this ZXcalculus is quite, it can be visualized in so many ways.
Yes.
Yeah, so it's quite nice. Is it better for the beginners to start with this kind of visualizations than, let's say, start with some classical approaches?
By classical, do you mean like?
I mean like standard ones.
Matrices?
Yeah.
The way that I would teach it, and I say this because actually my year-long part-time at IBM Quantum Education was building this tutorial on Intro to Quantum Computing that combines these two. So I'm actually of the camp that I think that there's different techniques involved, and I think that so my background was I had first learned this gate-based quantum computing, matrices, vectors, Rocket notation approach to the basics of quantum computing. So like the gates, the block sphere, these things. And I found circuit models, and I found some parts of it really esoteric. I wasn't satisfied with some of the examples. Or just I could compute the results, like say with the matrices, and see, okay, I do see that quantum teleportation sent analysis, data analysis qubit to pop, but I couldn't see. I didn't think that I wasn't quite convinced by the why. Right. It was actually this problem that it was the specific part I was conceptually trying to wrap my head around. When I did an undergrad project just for a course. This was actually when I studied abroad at the University of Cambridge when I was an undergraduate, and they have this thing called independent study, which is more to the UK undergraduate system, or like specifically Oxford and Cambridge, that isn't really a thing in the US. And so this is where we got, you could write a proposal for what you wanted to learn, and then they would find someone who could possibly teach you or work with you. Oh, okay. That was really cool. Yeah. And I came that up with my independent supervisor at the time, just a few months ago.
And who was your supervisor back then?
This is Dr. Carlos Lugo at the University of Cambridge. So he's, at the time I saw his website, his personal website, or just personal website, and then it said like biology, mathematics, chemistry, physics, and it was just like a circle, and it was like I do all these things. I was like, oh, that's so cool. Yeah.
So perfect match.
It was really exciting. So yeah, okay. I was in the middle of definition too. But these different axiomatizations. So it's not just different drawings. It's these choices have a lot of consequence in like in what you could do with them. We actually could even hybridize some of these axiomatizations. So I say axiomatization in that the graphical calculus gives you these sets of finite families of rules, and these rules are just this diagram could be equal to this other diagram. One of them could be in some context more complicated, more simple, and this is so I kind of first learned about it from the context of circuit optimization, where you have some complicated quantum circuit and you want to either optimize it to be shorter so you can run it better, or you want to simulate it better, and so you can plug in some input basis states and output basis states and get the amplitudes by simplifying the circuit until you get a number.
Right.
So these are these rules you could consider the axiomatizations of your calculus.
I see.
So it's quite more powerful to here's some. You could say you're breaking the abstraction of that's a term from linguistic computer architecture. You're breaking this abstraction of gates and moving into the algebras that are within these gates, or that really that I think it's much closer to what kind of makes these algorithms work. In fact, so these gate definitions can vary. I work most of my research is with qubits. So any finite dimension over spaces. So basically, if you have a qubit, it's like people say it's like you could represent a pure qubit state as like a 2-element vector.
Yeah.
It's just like the zero, like how roughly up to a couple of numbers, like the probability being 0 or 1. And for when I say probability, it could also be them at the same time.
Mixed state.
Yes. Or superposition in this case. And then you can have mixed states. I said pure states.
Right.
I didn't want to get it here. And then for qubits, it's just like a 3-level quantum system instead of 2-level for qubits, and then you can have higher dimensions. So I thought that was really cool to generalize. And so these different axiomatizations, like these rules, in diagram form, they kind of just generalize. And really, it's the algebras that this is drawing. They generalize well to all these to, for example, the Heisenberg Weyl generalization. The Pauli's and Clifford's will generalize to all prime-qubit dimensions. So I'm working on that quite a bit. And then but if you have the matrices, you get different matrix size for every dimension, and it just doesn't work in practice to work with the matrices. In practice, most quantum research it doesn't work with these matrices. So if it's taught with them, doesn't directly work with these matrices. If it's taught with matrices, it's kind of there's still more that needs to bridge this gap.
Who invented ZXcalculus? Do you know that?
Yeah. So the first paper, the story is actually. Well, let's see. You can probably also ask. There's a story that I think is quite consistent. Is that it's in a bus in Iran. Bob Kuka and Ross Duncan came up with this.
Oh, really?
Yeah.
In
2008.
Oh my.
So I don't know how young you were at the time, but that's a long time ago.
Yeah.
It's a long time ago. Yeah.
Wow. Okay, so basically, we covered 3 or 4 definitions. 2.
I can also just give you the definitions after. So it's these are just casual definitions, but it's maybe we're not giving the one after the other.
Right.
But the third one is a useful software tool for quantum computing applications, and there's many examples of applications. We cannot list all of them. There's 100. I don't know. There's way more than 100 papers on ZXcalculus and other graphical calculi at this point.
So when it became a hot topic, in the last couple of years or even prior?
Yeah, I definitely think I definitely believe that it's kind of 2018 and onwards. And there's a specific result, and that's the reason for this. So in the invention of ZXcalculus in 2008, and then around 2017 to 2018, it's in this gap, the kind of the biggest research problem at the time is completeness, something we call completeness of the graphical language. So there's kind of 3 notions of properties that you would want any graphical language to have across the board. One is soundness, but this one is kind of obvious. It's just kind of easy to prove. It's are your axioms correct? So, and also, can you, but more broadly, if you have a valid diagram according to the rules and the rules of composing different generators in the calculus, so if you draw a valid diagram, does it have a valid interpretation into in here? So these graphical languages are always working with interpretations in linear maps. So does it have a valid interpretation? So you can't draw an illegal or ill-defined diagram. You can't give the corresponding linear map for. So a linear map for. But you can have multiple different diagrams that correspond to the same linear. And then another is universality. And universality would be, I said linear maps, but you would be working with specific fragments. So, so for qubits, this would be 2-dimensional Hilbert spaces, and having, and then powers of them. And then so So in these linear maps, you can also have the universality property, which is that any linear map in the fragment that you're concerned with, that can be described in that can be described using a diagram. So you can always construct a diagram or find a diagram or even there exists a diagram that for every single linear map. So you could write down any diagram in your linear map, the concerned fragment you want to work with. And the last one's the hardest to prove by far. The last one is called completeness. And this is the precise expression that if you have any two diagrams that interpret to the same linear map, I say fragment, so you could consider like completeness for the stabilizer fragment of qubits, or you could think of like completeness for Clifford plus T fragment. You could have different fragments but this specific question I'm talking about is completeness of the calculus for all qubit linear maps on any number of qubits. So this is for all qubit quantum mechanics and mixed state as well. The mixed state one does follow well from the pure case. So the completeness for all linear maps on qubits is this result that was 2017 to 2018. And that was what really took off or kicked off this that people have been working on this calculus for just a decade, and not knowing if it's complete, and even some people who worked on the calculus were doubtful if you could have a finite set of axioms or a finite set of families of expressible axioms so rules in the calculus that could possibly you can derive from it all other rules. That's enough. You don't need to have infinitely many rules and keep searching for it. So that's I think a really big achievement that hadn't been reproduced in any other techniques. And so to me that is a major motivation for why from the perspective of people developing these calculi, this was a big deal. But some other reasons could be that a lot of interest was also that once you know you have all the rules you need, then you can confidently work on the applications and know I'm not going to be wasting my time trying to prove something that the calculus doesn't have enough to prove, because the calculus can in theory derive from that.
PhD student in computer science here at Oxford. What is your main research interest in your PhD talk?
My main research interest, I would prefer to say quantum computing, but of course that's probably true for most of the guests in your podcast. Thank you, by the way. And I think my main research interests are I think that it's hard to say a main interest because I'm quite interested in multiple different research topics, and there's a lot of intersections between them, and I can't say like one single word, or two words. But I think I started from the angle of quantum compilation, quantum circuit synthesis, quantum computer architecture. And I was interested in quantum graphical calculi, so I thought that there's a lot of advantages that formalisms can offer and very different techniques. So you can kind of convert between like graph theoretic techniques for like measurement-based quantum computing and the quantum circuit model, and show that the two are equivalent with these calculi. That was kind of what I had. That was my kind of first impressions when I first got here. And I was also interested in qubits, so higher dimensions. And actually, this definitely did not work for a good reason. Is that when I first got here, I was thinking, okay, maybe I want to write overcome all these qubit algorithms. Like, we have the qubit version. Let's just make the qubit version. It'll just be easy. And then I got here and I realized that people did not even figure out how to build qubit Tofflees. Like, not even the basic multi-qubit gates that you have. Like, people have not done that. Even though the qubit multiple control Tofflees has worked out, like, in fault tolerant gate sets for since before I was born. So coming here, so it just showed that there's a lot to learn and a lot to do. So I actually had multiple papers that work on building these qubit Tofflees and other controlled gates and all this fault tolerant gate sets in higher dimensions. And so that was really fun. It was really exciting because you have an idea what the qubit version looks like, and then you try to generalize it for all other prime dimensions or all other dimensions, and it's not easy because because you can't see how we're generalized. Like if you have qubits, okay, with bits you only have like two options, 0 or 1. And then with higher dimensions, there's all these different options and there's these different generalizations. So like even these three calculi I mentioned for qubits, like ZX, ZW, ZH, they generalize in multiple different ways with higher dimensions.
Right.
So we generalized, well, all those pictures not like, but so the ZX calculus just generalized for higher dimensions and all and all finite dimensions, and even I guess even infinite dimensions, but it depends on how you define it.
Yeah.
Quite straightforwardly. But some of the rules only hold for qubits or for certain prime dimensions. So we have so we've done the so writing a unique normal form for any Clifford diagram in prime qubit dimensions, and then you also have H calculus, and ZH calculus for qubits, phase 3, so without phases, the calculus just corresponds to Toffoli plus Hadamard gate set, what like the computations you can do and express in that calculus. And so but I looked up in the literature, if someone does find something on this, do let me know, but I could not find anything about prime qubit dimension versions or extensions of Toffoli plus Hadamard gate set.
Yeah.
And so maybe it's possible it wasn't a sensible question because I thought at the time, but maybe it's like quite a qubit specific notion to turn something on or off. But it does generalize, yeah. But I'm currently writing up a paper, so so I can't put you at anywhere yet. Right. But it was really exciting that you can still have new results even if people have been working on the theory of quantum computing for so long. I think it's a really exciting field that it's just many different. Right. Yeah, you can find new things There's a lot of new things to find.
For Quantinuum, as a research engineer, can you talk a bit about your work there and the projects you work on there?
Yeah. Actually, I'm really lucky in that for two reasons. One is that, or I guess, well, more than two reasons, but the two that came to mind is like one, I had wanted some industry experience, specifically just. So before that, my internships have been revolving around teaching and education, which is something I care a lot about. But at the same time, I also wanted to know. Starting towards the end of my PhD, I want to know what I should want to do after, and the answer is currently still I don't know. But since I've only joined Quantinuum for a few months ago, but I feel I've come very far with the team there since then of working together. And let's see. So yeah, being able to see industry and like also in person, just not being able to not just doing jobs on doing part-time work online, but actually having an office and people and like beer and pizza nights and things like that. And yeah. So yeah, that's one part. And another part is the second reason is I'm really lucky that this job is really related to my research. There's so much overlap. Sometimes I have to think about, okay, is this PhD thesis work or is this continuing work? But there's overlap in research collaborations, and thankfully I have the flexibility to do so. I actually feel that there's a lot of I feel that there's a lot of like open-mindedness in this decision about it. And so actually, something we've been working on there is the ZXW calculus. So this is the main project I'm on at Quantinuum.
So how is it different from the ZX calculus?
You take the Z spider, you take the X spider, and then that makes up the ZX calculus. You can have phases on them, and then and then you add that the W spider, which is like, so if you have just Z and W spiders, that's ZW calculus, and if you have Z and X spiders, it's ZX calculus. And what if you just put them in the same calculus? I mean, they're well defined, you can compose them, that's fine. They're just linear maps. But actually, you can get more than the sum of its parts. So you get kind of this I don't know if missing ingredient is the right word, but you get so if you have just ZX calculus, every time you differentiate a ZX diagram, you get just as you would in just numbers or functions. If you differentiate a function, you get like, say differentiate like function f times function g, then you get like f times g prime plus f prime times g, and then if you do that, you can also do that with quantum circuits. In fact, that's quite useful for like quantum machine learning. And if you differentiate a quantum circuit or a quantum diagram, like any linear map, what you get is sums of linear maps. But the problem is this sum was really annoying. It's something external to the calculus. You get if you differentiate the diagram, you get a sums of diagrams. So you get this diagram plus this diagram, and this plus is something that's not in the rules of this calculus. So immediately after you differentiate, you left the calculus. And to put it back in was not easy. You know, it's just not the way to do it. The way to do it properly is just have a generator that describes these sums, and that's where W spider comes in.
I see.
But the ZW calculus is also very useful on its own. It's also complete. You don't need the X spider. Like, the ZW calculus will probably, I think, so it's more applicable to like photonic quantum computing, like bosonic more general. So there's different axiomatizations that are going on, capturing different physics.
So what would you say are the fundamental concepts necessary to learn quantum computing?
Okay, so I can say this quite precisely because I've developed this tutorial. But some part of me is like this. I don't want to say perfectionist, but there's some part of me thinks that this work is not done. I think that I want to iterate and improve on it over and over again before I release the tutorial publicly. Although I'm happy to share it for that if people would like to give feedback.
Of course.
But because of that, I've thought a lot about this question. So I also learned quantum computing on my took some courses, but those are more informal or just kind of experimental, kind of first time offering these courses at UC Santa Barbara. And so, some of these concepts. So as I was learning it, sometimes the way it was taught was just not satisfactory or not enough for me to feel like I grasped the concepts or could then see how to apply it to other things. So I would say, I would say one, it definitely depends on your background and like your interest, what you want to do with quantum computing. Like, for example, most people who use computers nowadays don't need to know anything of what happens in the device or compilers or operating system level. Like you don't need to know that to use it. But I would say that kind of there's some general information that's good for anyone who works on quantum computing or use quantum computing to know. So I kind of combined in my tutorial. I kind of combined it's kind of this traditional so the tutorial is meant for people with a high school degree. So keeping that in mind, the prerequisites I say at the beginning of this about 100-page tutorial, about 60% of it is like quite just kind of fundamental. I say fundamental, but it's quite just definitions of the gates, of what is a qubit, what is the block sphere, the unit circle, and so involved in all that, you would need to know probability, just basic probabilities, to know like the norm of vector and this kind of thing. And you need to know like some very basic what is matrix multiplication, adjoint complex conjugation, transpose. There's like basic trigonometry to know where you are in the block sphere, and let's see. I think that's about it. So it also covers the notation of Rocket notation, but so that you don't have to know. Although many research learning uses do require that are out there. So, and then the kind of latter 40% of that tutorial, I would say, is with diagrams. So I personally learned and prefer if you first learn the underlying matrices in the qubit case, at least, so you have some frame of reference for what these diagrams are doing. Or at least if you're working with diagrams, to write down each initial when you're starting out, like write down these diagrams. Take their interpretation into the linear maps. But it's true that you could just work with the diagram and prove many things without going to the linear maps at the end or even ever. So,
would you say that linear algebra is the most fundamental field for learning the foundations of computation?
I think that's something people commonly say. I can see justifications for that. I don't know most fundamental. I think that's fair to say because you could think of any quantum computation, or it's just multiplying matrices and vectors, and but some I think it's important, but it's hard for me to say fundamental.
I mean, but for sure, it is one of the most important fields which you must learn in order to understand computation.
Yes. Although I will make a clarification, like I think that linear algebra at the kind of high school or early undergraduate level of like matrix multiplication is really necessary to do for anyone doing quantum computation to know what you're computing. But past that, like a lot of undergraduate or graduate courses in linear algebra, we cover most of what the course will cover would not be relevant for, say, someone working in quantum hardware or quantum materials. Like not necessarily that. So it's really hard to kind of come up with prerequisites for doing quantum computing, any aspect of quantum research because it's such a something I realize and just always amazed by is that it's so interdisciplinary. That I've met people from all these different fields and working on. Actually, we created I kind of helped create or come up with some ideas for some like kind of personality quiz of like what kind of quantum researcher you are. I just thought it was a cool project.
Wow.
And like I think I came up with 12 different roles you could have if you like what kind of like a BuzzFeed quiz type, but it's like what kind of quantum researcher are you? And it goes from theory to hardware to cryptography to quantum communication.
Can this test be found somewhere on the internet or?
Yeah.
Okay, so we will put the link into the description of the video later so that people can find it. What is your favorite programming language and why? Is it Python? Or Java or C++?
I think these are always quite loaded questions. Like, what's your favorite?
I mean, okay, you can we can formulate it and ask, let's say, what is the most useful programming language in, let's say, quantum world?
Okay. I think Python is still across the board just very commonly used. Many packages are doing that, so I think it's kind of quite. If people were deciding which programming language to learn, for Python would be the most beginner friendly for sure.
Because there's a lot. Qiskit is based on Python. And what do you think about Q#?
I haven't used it that much to be able to say just because in my research I've been mostly doing with theory stuff, so I haven't used quantum software that much.
And what would you recommend for the programming beginners? How to start with Python? Is it just watching lectures or programming on their own? So what is the best approach for learning Python?
Let's see. So I think it really helps if you have a goal in mind. Even if while you're learning like I think a hackathon or some other like place where you have a set time to do a set thing. I think it really helps to have a goal in mind because that motivates you to solve the problems. Because in programming there's a lot of problem solving, and so that really helps to kind of motivate you to write good code. Think about how to structure it and like what would the user want and like focus or like how can I make this better and like it. So hackathon is a good start.
And do you think that subjects like algorithms and data structures are necessary before getting into the programming world?
I don't know what you call the programming world.
I mean,
I think it's something you learn along the way. So even if you learn a bit the theory, sooner or later you have to get your hands dirty. So
you are the creator of Quantum Universal Education. Can you talk about the project?
Yeah. Although I guess I could say I was a creator, but it's really a team effort. Like it's many things. So it's kind of it is a Discord server. It's a website. We have some community events. We also host events with other people or listeners. it's going into so much because at the start I had just thought, okay, I want to. It started at the start. Motivation was I had made some course materials while I was an undergrad at UC Santa Barbara. For some reason, my college, the College of Creative Studies, lets you let undergrads propose course to teach other undergrads and officially make it on the registrar. So I'm not exactly sure why, but it was a really cool experience. Actually, I've also been to courses taught by fellow students as well. And I thought, okay, wanted to continue. I really enjoyed it. Wanted to continue. Just how can we help people get more involved in learning quantum topics? And it was also really inaccessible. So most universities don't have any kind of quantum computing course or quantum information course other than just the quantum mechanics. And it takes a really long time for that curriculum and courses to even be offered at first the graduate level usually, and then undergraduate, and then maybe high school. So many people just didn't have access and just have to learn on their own and just piece things together. And so there's a lot of questions that people would have. That's just, and sometimes you just need to ask someone who knows the answer, but they have to answer your question to get in touch with these things. So it was actually at Kiskit Global Summer School in 2020. That was this was right after pandemic hit, so this hit differently, of course. Like this was suddenly over 2,000 people online in a 2-week course.
Wow. That's quite a lot.
It was a lot. A large course. And it was just open and free to anyone. Those of us that joined that year, it was a really good experience, even though it's online with so many people. But I met some people through the course because there is a channel of their Discord server that lets for the Kiska Global Summer School 2020 that lets you make lets you just like make your own channels to meet people or contact your like subgroups and interests. And so one of them was I made a channel on quantum education. And I was just kind of curious. Wanted to meet more people who are also interested in education. And that was as much of the idea as it was. And we had one meetup from there, and that's just where it all started. Most of the people in that one call who just like people who cared enough about education just go to that one call. Like I'm still in touch with, and many of us are doing this quantum universal education. Like well, we just basically online, just only met online. Some of them never met in person. It's been years. And some of those I only met years later. Not just because of pandemic, but because we're living in different continents. Like it's just not even like continents. Like even continent like never been to. Or
do you believe quantum computers will be able to solve unsolvable classical computer science problems like P versus MP?
I don't know if it will solve P versus MP. I'll be kind of skeptical on this specifically because I don't think it's not that quantum computers would solve this. Even if it is, it's like humans who are using or want to use quantum computers are using like tools or formalisms or ideas from quantum complexity theory or something. I can believe that maybe quantum complexity theory is going like could lead indirectly to this kind of result. But it's hard to say. Well, quantum computers do X because it's really like humans who are using these quantum computers, and it's also not possible to know how something that is unsolvable is going to be solved. I don't know. I'm really skeptical. If you told me that you had a quantum computer that could solve P versus MP, I would say I would just not believe you. I would be like, like the crazy meter.
Okay, so what do you think about artificial intelligence and how do you compare it to quantum technology or quantum science?
Let's see. Comparing is definitely difficult. I think that it's come like really far in what we can do with AI. Just I remember like even growing up, like people had even talked about like machine learning winters. And so AI is like commonly compared to quantum technology. Quantum technology is the more up and coming technology that's kind of like on an upward trend as an emerging technology, but also coming after AI. So quantum in the quantum space, people like say social studies of quantum or other like analyses of like predicting quantum technology. And you could say people would compare to AI often, like in say like quantum ethics or quantum risks. People may say, these are some problems that we saw happen with AI as a technology, and quantum is prone to some of these problems as well.
Right.
Quantum machine learning is just as prone to the ethical dilemmas, maybe in some slightly technically different ways, but then as classical machine learning. So there's a lot we can learn. By we, I just mean people doing researching, working in quantum, who can learn from the kind of mistakes that were made in the AI space, from that angle. So that was the first thing that came to mind. You could also consider, let's see. So you could also consider quantum technology. It wants to. I mean, you could. It's just the trends of technology over time. Like quantum technology has a lot to live up to. Like kind of, there is hype. People would make projections about the technology, and so that's a bit different than AI. People don't quite. It's not so much as like a trend. In fact, there's noticeable moments in AI where like the state of the art just suddenly jumps. Yeah.
And do you think that the hype around quantum is justified, or?
It definitely depends on which parts of the hype. There's definitely some parts I don't think are justified. There's some parts I think are under, maybe are not overhyped. Yeah. So it depends on which parts. But maybe I won't say which ones.
Yeah, of course. Okay, so do you have a role model in science? So
yes.
It can mean any field.
Yes.
Okay.
But I tend to find role models and I would say mentors is a better word. So it was kind of hard for me to abstract or kind of to role models who were just people. I found it easier to look up to people who I imagine can ask questions and just really learn from a lot. That's the primary way I think of generalized. It's just a lot of I've had a ton of like mentorship or advice to even be anywhere near here. So, so yes, like I've had really good mentors who really wanted me to succeed.
About the University of Oxford as an educational and research institution, and how do you compare it to the U.S. universities?
Wow. So actually, quite a bit of this comparison. It's just different systems. It's the way that they run the universities. U.S. and Canada have like similar systems because many universities are the same larger organization in the U.S. and Canada, and then it's just completely different system or rules or bureaucracy on the other side of the world. It just the system is so different. That was such a not just culture shock, but just adjusting to. So even just in the U.S. in physics, for example, most undergraduate physics students, it's more common to go from undergraduate to PhDs. So there's not as many master's physics programs, I would say, or it's just gotten more common recently. But there's still plenty of physics master's programs. But in Europe, actually, it's required to have. So Europe, non-UK, but it's required to have a master's to even apply to most of the programs.
Right.
And PhD students in Europe are treated as employees. UK is kind of in the middle of this. You don't need to have a master's to apply, but if you don't have one, then it would make the application really difficult because you're competing against people who do.
Yeah.
And then the UK PhD students are not considered employees, so don't have those rights. But I think the teaching contract is friendlier in some UK universities than the US or Canada universities in terms of how much teaching. So there can be there's a quite big difference. Funding, the way that funding works, is also completely different. Anyway, so I actually we compare actually YouTube video about 2 hours long. It was actually a workshop we did live and record. Me and 3 others from Quantinuum Universal Education. The 4 of us had applied to master's and PhD programs in 6 different countries. And so that the kind of full thoughts and comparisons and like experience learned this kind of stuff. That all that gems is like there. So I can't reproduce it here. It's just a short amount of time. But
and how would you compare living in the sunny California and in the cold and rainy UK?
Sometimes I feel a bit weak because I just see that it's raining. I'm like, oh no.
It's raining.
I'm just not used to it because not only I lived in California my whole life before this, but I did my undergraduate at UC Santa Barbara. It's a beautiful university with a mile of beach on campus, and nothing after that will compare. Oxford is really beautiful. There's all this architecture. It's a lot of character to Oxford, but it's not beach every single day, always in the background. You can't unsee it. So that's my personal zero world problem. Like I miss the beach.
Right. Okay, so what are your plans for the future? Do you have any? Would you rather stay in academia or perhaps work in computers?
Let's see. It's quite frankly, I haven't been planning ahead that much. In that I'm exploring things as I go. So actually, when I first became interested in quantum computing, I would say it's like early 2017, maybe. So this is even before the Google quantum supremacy paper, and I think that was one of the that caused media interest and just public interest in quantum computing. It just exploded from there. I think if I had to name one moment or point in time that exploded, I would pick that point. And so, but even then, quantum is such a new technology, so it's hard to predict what's going to come. And I think that at some point you do have to step back and just let things happen. I think I've been told, or I did ask my mentors of what their advice, just so I don't want to go completely down some wrong roads or something. But and what one of my mentors just told me, he thinks I'm doing the right thing. I'm just exploring what it's like to do research in academia and to get a taste of what it's like to work in the industry. So this is I'm still processing this information. It's a long computation, I'm kidding. But I just started working research in industry a few months ago. I really enjoy it, but I just also really I think I just enjoy research, so that's the only thing I'm quite decided on.
Perfect. So, is there anything else you would like to add for our viewers? Maybe some advice or something. If you
I think one piece of advice is I think this is for me my number one piece of advice to give is that to someone starting out, I think oftentimes it can be really intimidating. Both computer science, physics, math, quantum information is can get very technical, but and so because of that, there's a quite steep learning curve. In fact, there's many learning curves because there's so many different, again, a mistake that I personally made, or not mistake, it's a good mistake to make, but I meant, it's not productive. And productive is to say, when I first started out, I wanted to learn, anything quantum. I wanted to learn more. This is all new to me. It was really fun. But you feel like you don't understand many things because, in fact, the deeper I feel, I think something that I think it would be definitely helpful for me to hear is to know that quantum computing is extremely interdisciplinary. There's just quantum technologies in general. There's things that anyone can do. There's things that there's people have really different skill sets, and some people with quantum have almost no overlap in their skill sets. You could get two experts in very different fields of quantum and have them in a room talk to each other. Probably wouldn't get very deep in the conversations. They just don't the stuff they work on don't have that much overlap. Just so many different pieces to this puzzle, and it's not a one-man effort to build a quantum computer. Not at all. It's all these different components. We have no idea how And if they will fit together, we know that we're getting better at putting them together over time. At least that's a good thing. But I think that's some interesting.
Perfect. Lia, thank you so much for this conversation. I really enjoyed it, and I really wish you all the best for your career. And hopefully, we can meet some other time as well and talk on the podcast.
Thank you.
Thank you so much.
For inviting me. Hope you enjoy.
Thank you. Perfect.